Last time we talked about energy uses and sources of energy, whether that be renewable or non-renewable sources of energy. We talked about the origin and consequences of nuclear energy, as well as alternative energy sources as sources for jobs for people. Today, we're going to be discussing solid and hazardous waste. And here's a photograph that was taken by Professor Unger with plastic waste along the shoreline in Bonaire. So garbage is something that most of us really don't want to think about. It's messy and smelly, pretty much a worthless liability that we just tend to toss away and never give a second thought to. But garbage has also been with us through the dawn of civilization. It's unpleasant, it is disease-ridden, it generates middens of food waste or animal bones, and all of this has occurred just on the edge of town, typically. So modern civilization improved this system by burying garbage in piles. We concentrate the disposal of our trash into fewer and larger, quote, better built sanitary landfills. These landfills you probably are familiar with looking something like this. We understand them to be vast and expensive to manage and really taking up a whole lot of area. But these tend to not be within the sight of people living near these trash heaps because really nobody wants to be around them. And so often these are hundreds of miles away from the cities that produce the trash that ends up in these landfills. So to start off, we're going to be discussing a case study of a waste-free city that's located in Sweden. This waste-free city case study is outlined in your textbook in chapter 14, so please go ahead and give that a read. But basically, this city is called Kristianstad, and it has embraced its garbage. This southern Swedish city has turned an unpleasant liability into a money-making resource. So how did it go about doing that? So about 20 years ago, Kristianstad faced all the usual waste disposal challenges of a mid-sized city. Basically, there was growing volumes of people, which of course led to growing volumes of trash. And this increased the cost of trucking that trash from the city to the landfill. There were also, of course, concerns about the smell and air quality as well. At the same time, Sweden had committed to reducing greenhouse gases and fossil fuel dependence with an eye toward mitigating climate change. And so they came together to create a less vulnerable energy future for themselves. So most notably, the city built a biogas plant on the edge of town. The way these digesters work is the biogas digesters takes organic waste like household food waste, effluent from food processing and slaughterhouses, even manure from local farms. It then mixes all of that organic waste together with water, and it lets the slurry digest for about 3 weeks. So submerged in that liquid mixture are bacteria, and the bacteria drive the biogas production mechanism. So this happens in the absence of oxygen, which allows the buildup of methane that is produced by those methanogenic bacteria. These are the same methanogenic bacteria that we discussed that live inside cow guts and let them burp and fart out methane. And so this methane that is produced, it is the biogas that is produced. It's high quality fuel that can power vehicles, run electricity generating plants, and provide heat to the town's homes. So undigested solids are redistributed on farm fields as sterile, disease-free, odor-free, and weed-free fertilizer. So really they're allowing this cycle to occur where the people are generating waste from food products, even agricultural products. All of this ends up in this biogas plant where it produces that methane with the aid of those methanogenic organisms. And that methane can then go on to be fed back into housing, to provide heat to those citizens, also provide fuel for vehicles, or for the undigested materials, provide fertilizer to then feed back through this entire cycle. So Kirstenstad is considered a waste-free city because it produces methane from their sewage and the cycle repeats itself. The Kirstenstad landfill and sewage plant pipe methane to a district heating plant, which provides hot water for household heating. Interestingly, in addition to household heating, it also fuels a regional bus fleet. And this is the most visible aspect of this waste to energy system. Over 2/3 of the nearly 1,034 city and regional buses now run on this biogas. So how was this made possible? Well, basically, who developed this technology? It was engineers, physicists, biologists, and environmental scientists, all coming together in an interdisciplinary way to solve a problem and make Kirstenstad a waste-free city. So this just goes to show you what can be done with an interdisciplinary approach where scientists and engineers from very diverse backgrounds come together to solve a shared problem. Another thing that is increasingly drawing attention of biologists, microbiologists, and environmental scientists is how we can harness the power of those microorganisms in another way. So we're going to watch this video.
We created a mutant enzyme that eats plastic bottles.
This sounds fantastic, doesn't it? Well, the breakthrough offers promise in solving one of the world's biggest pollution problems. Kathy Walsh went to NREL to meet the brains behind the breakthrough right here in Colorado.
That's right. And this discovery was made by researchers both in England and at the National Renewable Energy Laboratory in Golden. It may be the recycling solution the world desperately needs. It's a stunning discovery that could drastically reduce plastic pollution. Researchers at the University of Portsmouth in England and across the world at the National Renewable Energy Laboratory in Colorado were examining a natural enzyme found in a Japanese recycling plant that could break down plastic. At NREL, study leader Greg Beckham says scientists genetically modified it.
Essentially to break it, to take it backwards in evolutionary time, and we accidentally made it better.
A test on smooth pieces of plastic from one of Beckham's soda bottles revealed the scientific surprise.
It's pretty cool.
Senior scientist Brian Donahoe explained how the enzyme eats away at the strong, man-made plastic.
Carving out these pits and cavities down into the surface.
These images were magnified and sped up to show the enzyme at work. It usually takes decades, if not centuries, for plastic bottles to break down.
And I think that we're on the order of months here instead of decades.
Does this solve our plastics pollution problem?
Absolutely not.
But scientists call this a promising step. Will this change the Earth?
Eventually, I mean, this is a change we have to make, I think, right?
Scientists are now working to improve the enzyme to work on a large scale. And there is, of course, urgency in this work. According to NREL, experts estimate that by 2050, there will be as much plastic waste that is in the ocean by mass as there are fish.
You know what I think is so beautiful is that enzyme was right here all along.
Yeah.
Just had to find it and cover it.
Actually, they had to do a little work, and amazingly, it was accidental work that found it.
That's incredible. All right, thanks, Kathy.
We remain on weather alert.
So that just goes to show you that in science, you have to keep a very open mind and just welcome any possible new discoveries that you might happen upon. So now let's talk about how to define zero waste. In 2015, there was this meeting. It was called the United States Conference of Mayors. And as the name suggests, it was just a conference or a meeting of different mayors across the United States. They came together under the umbrella goal of defining zero waste for their cities and trying to understand how they can actually implement practices that can make them zero waste. So on the tartan, I have provided to you this article called How Communities Have Defined Zero Waste. So please go ahead and read that. It is from the EPA.gov website. But in this meeting, they adopted a resolution to define zero waste. And we'll get on the next slide what those definitions were. But also during this meeting, they called upon federal and state governments to recognize the rights of local governments to enact ordinances that support the strategies to reduce waste in their local communities as part of a comprehensive zero waste strategy. So they basically said, hey, we're willing to put in the work. We have these ideas that were developed in consultation with environmental scientists. And we call upon the federal and state governments to give us aid, assistance, and support in meeting those goals. So what were those goals? How did they define zero waste? So here in their document, they outline a number of different things. Number one, extended producer responsibility and product redesign. In other words, let's hold those people, those industries accountable for producing the amount of plastic and waste that they do, and also implore them to redesign their products such that they're not producing so much waste, particularly plastic waste. Number two, reduce waste, toxicity, consumption, and packaging. All of that rolls into the first bullet point here. Number three, repair, reuse, and donate. That falls upon the consumer to take responsibility to seek out products that they can potentially reuse. And if it has no reuse potential in their household, then donate that item. Don't just throw it into the landfill. Number four, recycle. We'll talk about recycling in this lecture in coming slides. Number five, compost your organic waste. We'll talk about composting as well. Downcycle and beneficial reuse, meaning let's see how we can repurpose those items that we bought previously for perhaps another purpose. Waste-based energy as disposal. This goes right back to that waste-free city in Sweden that we talked about in generating biogas from our refuse that we just toss into a landfill. And then finally, landfill waste as disposal as well. So the question is, what waste do we produce? We all produce, as individuals, unwanted byproducts in nearly everything that we do, from eating lunch to driving our car to work or to school. According to the EPA, the US produces 11 billion tons of solid waste each and every year. And if we were to break that down to understand how many an individual is producing, that's about 3.6 tons per person each and every year of waste that we are producing in this country. There is industrial waste. This is other than mining and mineral production. This amounts to some 400 million metric tons per year in the United States alone, all of that falling under the umbrella of industrial waste. We also have municipal solid waste, which is probably what you're more familiar with. This is accounting for nearly 250 million metric tons each and every year. Municipal waste is considered to be anything that is produced as garbage in our homes, our offices, and our cities. And this accounts for a small percentage of total waste, but it's hard to reuse and recycle because it contains many different materials. And as we'll learn when we're talking about recycling, it is that mixing of materials that makes it really hard to repurpose and recycle this trash. So now for some good news and bad news regarding solid waste removal. We have a chart here that shows the year on the x-axis going from 1960 all the way through 2015. And these are the waste generation rates that are shown in total MSW or mass solid waste generation in millions of tons. So in the red, we have total generation. And then in the blue, we have per capita generation or per individual generation. And so you can see that from 1960 through recent times, we have slowly increased the amount of waste generation per capita. But since the year 2000, we've really just remained steady, which is really good news. However, when we take a look at total waste generation from the year 1960 through more recent times, we see that we've steadily increased. And again, it's starting to level out again here. So now let's take a look at the rates of recycling. Here we have again on the x-axis from 1960 all the way to 2015, the years. We have total recycling in millions of tons on this y-axis, and then we have percent of generated recycling here. So we can follow in red the total amount of material recycled, and we see that there's a huge uptick in the year 1985 in the amount of material that has been recycled. We can also take a look at the percentage recycled and see that at that same year, we do reach an inflection point as well. So from the year 1960 through the year 2010, we went from recycling about 6% of our materials to about 34% of our materials. So that is a considerable gain in the amount of materials that we are recycling. But despite that considerable progress in the past 20 years, we still only recycle about 30% of our glass bottles and jars and less than 50% of aluminum drink cans. It gets even worse when we're talking about plastic food and beverage containers, which is about only 7% that we recycle. We could stand to save a whole lot of more money, energy, land, and other resources if we could just improve this recycling rate, which we've shown that we absolutely could do. So what is responsible for this increase in recycling and decrease in the amount of waste that we've been generating as a country? And so the trends in waste generation follow technological trends. The material and products that we use in our daily lives have considerably evolved, especially within the past couple of decades. And so per capita waste generation is down about 8% since the year 2000, affecting recycling, landfilling, and waste to energy. What we're seeing is the use of less paper because we have technological devices like computers and phones. We're also seeing, instead of metal being produced for all of these various items that we would use on a week-to-week or day-to-day basis, we're seeing more plastic instead, and there's no growth in metal needing items. So this is an image that shows, just about 20 years ago, all of the different devices that you would have needed to do your work, your telecommunications, your video capture, your GPS coordination, your recording, and your photography, not including your watch and your hard drive. All of these different items are now housed within one device, which cuts down on the amount of materials that are needed to generate all of these different devices. Let's talk about the waste stream. The waste stream is basically everything that we throw away. It's a term to describe the entire life cycle of the garbage that we produce, from putting out the trash can and recycling for pickup to landfilling, energy production, and the reuse of recycled materials. So many of the materials in our waste stream would be valuable resources if they weren't mixed with other garbage. But unfortunately, our collecting and dumping processes mix and crush everything together, which makes separating those more valuable items from the less valuable items extremely hard to do or impossible to achieve. Our society needs to make more responsibility for the waste we create and not just simply allow us to toss it and forget it. So what is in this waste stream? We have the composition of municipal solid waste in the United States by weight on the top graph here, and by disposal methods on the bottom graph here. So amount generated by weight, we see that we have organic materials like yard trimmings and food waste. We also have wood waste and sewage sludge. We also have junked cars or worn out furniture, and our consumer products like paper and cardboard and plastics. In addition, there are newspapers, magazines, packaging, advertisements, and paper office refuse. But again, only 34% of all of this trash is recycled. So there is this old ecological maxim or saying that everything goes somewhere. Just because you never see it again doesn't mean that it has been destroyed. It exists somewhere else. One of the waste disposal methods that we use, particularly in our landfills, is this open air disposal method. Open, unregulated dumps are still the predominant method of waste disposal in most developing countries. Most developed countries actually forbid this open dumping, at least in urban areas where there are people living. But of course, if you go to these cities, you can still see that there is illegal dumping that is occurring. So it's not just a aesthetic problem where, you see a bunch of trash and it's really annoying. No, most of this trash washes into sewers and then into the oceans. And so often this illegally dumped garbage includes waste oils from cars or solvents, unfortunately polluting the ocean through this runoff that runs through this dumped material into the ocean. So this illegally dumped garbage often includes toxic chemicals, which show up in the groundwater as well, unfortunately. So there's an estimated 200 million liters of waste motor oil that are poured into the sewers or allowed to soak into the ground every year in the United States. This is about 5 times as much that was spilled by the Exxon Valdez spill in Alaska in 1989. And what's really striking is that no one actually knows the volume of solvents and other chemicals disposed of by similar methods. So it's still a huge question mark how many toxic chemicals are actually in our groundwater. Unfortunately, ocean dumping is mostly uncontrolled. The oceans are vast, but they're not large enough to absorb our waste without harm. Each year, about 55 million pounds of packaging, including 500,000 bottles, cans, and plastic containers, are dumped out at sea. And so even in remote regions, beaches are littered with non-degradable flotsam and jetsam. And so that will point you to the cover photo at the intro of this lecture. So until recently, many cities in the United States, they dumped their municipal waste, their industrial waste, their sewage and sludge into the ocean. It also includes a lot of fishing gear that's just discarded at sea by the fisheries industry. So more than 660 miles of nets are lost or discarded at sea each and every year. And as you can imagine, that spells disaster for natural fish and wildlife populations. And so federal legislation now prohibits this dumping, especially in New York City. They were the last to stop this offshore sewage sludge disposal. It finally ended in the year 1992. One known problem of this vast dumping of refuse into the ocean is the Great Pacific Garbage Patch. We've already talked about this garbage patch in previous lectures, so I want to end the discussion on this on a little bit of a high note, but just to review, that Great Pacific Garbage Patch was discovered in 1997 by a sailing captain named Charles Moore, and it's the best known of these plastic debris fields. It's actually not the only one in the ocean, it just happens to be the most known. And so in all the world's oceans, there are vast circulating currents known as gyres that are driven by Earth's rotation and the Coriolis effect. And so those gyres tend to collect materials and refuse from all across the globe. So these currents, they collect that floating plastic debris. Most of it actually are in tiny fragments or microplastics. And this can be collected in regions that's thousands of kilometers wide. So the North Pacific gyres captured at least 100 million tons of plastic. Efforts are ongoing right now to clean up this plastic. But as we saw in that news report, there are active researchers right now trying to understand how we can harness the power of microbes to degrade that plastic with the enzymes that they produce themselves. And there's research ongoing right now at UT to help develop that technology of microbes degrading plastic. I also have a friend who is creating right now biodegradable plastic. So really it's just within grasp to get rid of this plastic dependency that we have in the United States and across the globe. As I mentioned, there is hope for the garbage patch, and I really want you to watch this video that I linked to on the tartan. It's called The Ocean Cleanup Celebrates First Haul of Plastic from the Great Pacific Garbage Patch. So let's talk about landfills again. Landfills receive about 54% of all US municipal solid waste, and a modern sanitary landfill is designed to contain that waste. Operators are required to compact the refuse and the trash and then cover it every day with a layer of dirt. This covering really helps to decrease the smell, and it discourages rummaging from insects and rats. So this method in this sanitary landfill condition helps control pollution, but the dirt also takes up as much as 20% of the landfill space. So since 1994, all operating landfills in the United States have been required to control such hazardous substances like oil, chemical compounds, and toxic metals. That's because these things, they tend to seep through the piles of waste along with heavy rains. So to prevent that leakage of toxic substances to the groundwater and to nearby streams, landfills require an impermeable clay and/or plastic lining. And so these linings help protect our nearby streams and our groundwater from the trash that's in these sanitary landfills. So these landfills, they have to also manage methane. That's because methane is a very powerful greenhouse gas that's produced when organic material sits inside of a landfill. It's created again by those methanogenic archaea. And methane is such a thing to consider because it's about 20 times as potent of a greenhouse gas compared to carbon dioxide. So landfills in the United States are the single largest anthropogenic source of methane, which is new to me. I didn't know that. And so globally, landfills are estimated to produce more than 700 metric tons of methane annually. So in some cities, they're able to harness that methane as fuel, again, using it as a biogas source. So now about half of all landfill gas in the United States is either flared or burned on site, or it can be collected and used as fuel for electric generation. And this electric generation actually is pretty economical. And some landfill operators are deliberately pumping water into their waste as a way of speeding up the production of methane. And so this is how it works. You have your trash here. You also have your methane pipes and collection wells. And then over here, you have where the burning happens. So in the trash heap, the trash decomposes in the landfills, creating that methane gas. Methane, of course, is a gas, and we call it a fugitive gas, meaning that it wants to leave whatever source that it came from. So it is harnessed by these gas collection wells. So as that fugitive methane gas tries to escape, it's collected in this well system. It rises to the top of the landfill and it's collected in these pipes. The methane is then shuttled over here to be burned to generate heat, or it can simultaneously be used to generate electricity. And I'd love for you to watch this YouTube video that describes this process in detail and how to turn trash into cash. What else do we do with our trash? We also tend to export it to countries outside of the United States, other countries who are unfortunately ill-equipped to handle such waste. In 2006, for example, 400 tons of toxic waste were illegally dumped at 14 open dumps in the capital city of the Ivory Coast in Africa. And so most industrialized nations agreed to stop shipping hazardous and toxic waste to less developed countries in 1989, but this practice still continues. Again, as I just mentioned, in 2006, that 400 tons shipped to Africa. So most of the world's ships are obsolete, unfortunately, today, and they're now being dismantled and recycled in poor countries. Unfortunately, this work is very dangerous, and old ships are often full of toxic and hazardous materials. Another thing that we have to consider is discarded electronics. There are at least 2 billion television sets and personal computers in use globally. Televisions are often discarded after only about 5 years, while computers and gaming consoles and cell phones, they are becoming obsolete even faster than that. So it's estimated that about 50 million tons of e-waste are discarded each year worldwide, and only about 20% of those components are currently being recycled. So we are producing a whole bunch of discarded electronics, otherwise known as e-waste, and that is one of the greatest sources of toxic material currently going to developing countries. These e-waste contain things like lead, mercury, gallium, selenium, arsenic, but they also have valuable materials in them like gold, silver, copper, and steel. So it's again, it is having the equipment and the wherewithal and the resources to effectively recycle and reuse those valuable components, which unfortunately, most of the countries that we ship our e-waste to do not have.